Okay, welcome everybody to the next talk of today. This will be a talk by Professor Jerzy Kaczorowski. Let me say a few words about him. Jerzy Kaczorowski is a full professor at the University of Poznań and a member of Polish Academy of Science. He does research in analytic and algebraic number theory. His work contains a number of great ideas which had a significant impact on number theory. In particular, he has important results on L functions that have already been present at our workshop in the second talk of the workshop. I hope you recall, you remember the talk by Bartosz Naskręcki. There were L functions, and Professor Kaczorowski has results about Zellberg class structure of L functions, and he spoke about that at the Institute of Advanced Studies at Princeton. Also, Professor Kaczorowski is an author or co-author of 120 papers, around 120 papers, published in, some of them published in the most prestigious journals like Annals of Mathematics, Invenciones, and Acta Mathematica. He is the editor-in-chief in Acta Arithmetica and Functiones Approximatio, and as well as editor in a few other journals. He received a number of grants and rewards for his work, in particular Sierpiński Medal, Sierpiński Prize, and the Prize of Prime Minister for Outstanding Achievements. And finally, we are more or less of the same age. And when I think number theory, I think Kaczorowski. I have just been raised on that. Please, the floor and Zoom is yours.
Thank you. Thank you so much for this nice introduction. Okay, title of my work is displayed in the screen. I will talk on analytic methods in arithmetic. In fact, that means I will talk on analytic number theory. So let me, oh, it doesn't stop to work. We cannot change the page. This should be switched on somehow. Now it works. Okay, so analytic number theory is a branch of mathematics where arithmetic problems are studied using analytical methods, coming from harmonic or complex analysis mostly. Number theory or arithmetic is study of integers and their generalizations like manifolds, algebraic manifolds, in particular elliptic curves, but they are discrete structures, no topology, no non-trivial topology. And analysis, in contrast, is study of continuous structures. We use Fourier series, Fourier transforms, smooth and holomorphic functions, and these objects have non-trivial topology. And one can ask how it's done, how it's possible that we can study arithmetic discrete structures using continuous structures or analysis. So let me start by explaining this phenomenon. So in general, let G be a locally compact abelian group and T1 the unit circle, so set of complex numbers of modulus 1. This is, of course, a compact abelian group. A continuous homomorphism chi from G to T1 is called a character of G. And G hat is the group of characters, the dual group of G. It has, of course, structure of a group. In fact, when G is locally compact, G hat is locally compact as well, and abelian also. And G discrete means that G hat is compact. So this is this kind of duality between discrete and compact structures. Okay, this works in two directions, of course, and dual of the dual is back the original group. This is Pontryagin duality theorem, quite important in harmonic analysis. So for arithmetic, the following special case is important. G, the additive group of integers. Of course, this is a discrete group, topological discrete group, but the dual group of characters of Z is T1. And dual group of T1 is Z, according to Pontryagin duality. More explicitly, characters of Z are functions like here. Yeah, they are given by this formula, where T is fixed. Of course, T can be, yes, okay, can be think of like modulo 1 because of periodicity of complex exponential function. And the map sending chi to value of chi at 1 is an isomorphism of topological groups. The characters of T1 are given by the following formula. It's just rising to the nth power, where n is an integer, and the map sending chi to n is an isomorphism between hat of T1 to Z. So the general principle is the following. A problem with integers is formulated in terms of the dual group, T1. And this group has much richer analytic structure. Then we solve this problem in T1 using typical analytic tools. Let us look at an example, the Goldbach problem. The Goldbach problem or Goldbach conjecture is the following one, that every integer greater than 2 is a sum of at most 3 prime. Well, let n be a positive integer, and let us consider the following sum. S alpha, summation is over primes up to n of the values of complex exponential function. In fact, you see, this is the sum of characters of the group Z, so character sum. When we denote by Rn the number of representations of n as a sum of 3 primes, then the third power of our character sum is another sum of characters with certain coefficients. And when n is less or equal to n, the coefficient is exactly the number of representations of n as a sum of 3 primes. In particular, Rn of n is Rn. So Goldbach problem can be reformulated in the following way to show that this coefficient In of n is non-zero, it's positive. If it's positive, then n is a sum of 3 primes. We can compute this by Fourier formula. Rn is just a Fourier coefficient of this third power of character sum. And let us notice that at this moment we switch to the dual group because integration from 0 to 1 is in fact integration of a quotient group of R over Z, which is the same isomorphic to T1. And it's possible to compute this integral. This is a non-trivial task, but possible. And the result is as follows, that of course, this is not exact for a computation, but we can, well, give an asymptotic formula for this integral when n tends to infinity. So the main term of this formula is here, is sigma n times n squared over square of log, and sigma n is given here as a complicated product, plus a reminder. Then attention that here this exponent 2 and this exponent 4. That means that the main term dominates when n is large. This main term is bigger than the remainder term, and so starting from certain point on, this quantity is positive, tends to, in fact, tends to infinity. Okay, the sigma n is called a singular series of the Goldbach problem. So for odd n, singular series is greater than 1/2. For even n, it's 0, because when p is between the divisors of n, we have one factor equal to 0. But for odd n, sigma of n is greater than equal than 1/2. So really this term here, the main term is positive, it tends to infinity much faster than the remainder term. In that way, Vinogradov in 1937 showed that there exists a knot such that for every odd integer greater than a knot, the sum n is a sum of 3 primes. This was a great achievement. So this is half of the Goldbach conjecture for almost all n. Now this original proof of Vinogradov gave this astronomical value of n naught, which is 3 to 15. So it is impossible to check by computer if remaining that the initial integers are in fact sums of primes. But in 2013, Harald Helpgott was able to prove Vinogradov theorem with n not equal to 7. So nowadays we know that all odd integers greater or equal than 7 are sums of 3 primes. Okay, this was illustration how Fourier analysis can be used to study arithmetic problem. But where do the functions of complex variable come from in arithmetic studies? And in particular, why functions like the Riemann zeta function or generalizations of these natural objects in number theory. So again, let us look at the following definition. A continuous homomorphic Q from G to multiplicative group of complex numbers is called a quasi-character of G. Again, this is the group, a larger group than group of characters, group of quasi-characters of G. Group of quasi-characters of Z, of discrete group of integers, is Z plus, so the group, additive group of complex numbers. And this is isomorphism of topological groups. So this partially answers this question, but not completely. In practice, quasi-characters of larger groups than Z are used. In fact, we use ideal groups of algebraic number fields, but it's no time in this short lecture to enter this matter with details. So let us look at the following more heuristic approach.
Just a quick question. Do we have also Pontryagin duality in this context of quasi-characters or no?
No, we do not. Okay. The heuristic approach is as follows. Let A be an algebraic object in general. For number theory, it can be algebraic number field, finite extension, algebraic curve, defined over K, or an algebraic manifold over K. For every prime ideal P of K, let AP denote the corresponding localization, so the local algebraic geometric structure. And suppose that in some natural way we can associate to P a local zeta function, LP of S, which is meromorphic on Z and holomorphic for all S with sufficiently large real parts. If the product over all prime ideals of these local vectors converges in a half plane sufficiently far to the right, we can define the global zeta function associated to S to A as follows, just taking the product of local factors. And this is holomorphic whenever product is well converged. And if this global object has good analytic properties, it's called an L function. I will explain in a moment what good analytic properties means. A generalization is also important in number theory. We consider a pair, an object, arithmetic object, and a group associated to A. For instance, A could be a number field, and the group could be the Galois group, K over Q. And we consider representation of this associated group GA and define the global zeta function associated to A and the representation as the product of local factors. So the pattern is as before. What good analytic properties mean? Good analytic properties means that there exists a meromorphic continuation to C. So initially, an L function is well defined in a half plane, right half plane, but we need that it has a meromorphic continuation. So analytic continuation to a meromorphic function, and has a finite number of poles, so it is not wild function. And also it has restricted growth. So, for example, we need finite order of polynomial growth on verticals, and a very important property is functional equation of the Riemann type, possibly with many gamma factors. General pattern is as follows. We need to study algebraic or arithmetic properties of A. We switch to an L function, and we hope that this L function contains information on the main object. And we study analytic properties. And for studying analytic properties, we have complex analysis with many very well established tools. We can prove many things about L functions and then look what do they mean for the initial algebraic or arithmetic problem. So let us look at an example. Let our A be the field of rational numbers. For every prime number P, let QP be the corresponding field of p-adic numbers. Then ZP, let ZP be the ring of p-adic integers. UP is the set of p-adic units. VP here means p-adic valuation. We have that multiplicative group of p-adic numbers is the sum of the shifts, multiplicative shifts of group of units. And all of them are local compact abelian groups. And therefore there exists a measure on the multiplicative group of p-adic numbers, UP star, such that it's normalized on UP. Okay, UP is compact, and therefore our measure of compact group, every compact group is finite. We can normalize it to be one, and this is uniquely then determined. Then the local zeta function is defined like this. This is so-called Mellin transform with respect to Haar measure on ZP, on the ring of p-adic integers. And this converges from real part of S greater than 0. Real part of S usually in analytic number theory is denoted by sigma. I don't know why, but it's okay. Everybody do this. We also will follow this. Okay, so we have the local factor, and let us look. Let us compute simply this local factor. So integration is over ZP, and ZP is this sum of the disjoint shifts of UP. So we have sum of integrals, and on every such shift, valuation is simply P2 minus K. So it's really trivial computation, and measure here, V star measure of UP is 1. So we have arithmetic progression, and this is 1 minus 1 over PS minus 1. So this is local factor of this p-adic situation. And so the global zeta function is the product of local zeta function or L functions, and looks like this. This is famous Euler product of the Riemann zeta function. And this product converges for sigma greater than 1, real part of S greater than 1, and represented for a holomorphic function on this plane. let us see that, let us notice that the fact that Z is a unique factorization domain, so that every natural number can be uniquely determined as the product of primes, up, of course, up to the order of the factors, is equivalent to the statement that Riemann zeta function defined as a product is equal to the sum from n over n, from 1 to infinity, 1 over n to s. This one here is the number of representations of n as a product of primes. And because this is one, that means that we have unique factorization. So this is just a very simple example of the fact that something, analytic object, Riemann zeta function associated to Z contains some non-trivial information already here from the definition, just from the beginning. Okay. Riemann zeta function has many interesting properties. It has analytic continuation to C. The only singularity is a simple pole at 1 with residue equal to 1. S minus 1 times Z of S is an entire function of order 1. And zeta satisfies the following famous functional equation with one gamma factor. Another example of interesting L functions is Dirichlet L functions. For every Dirichlet character mod Q, we associate the following product. So in that case, this is this local L function can also be defined as a Mellin transform over a certain periodic group. And if K is primitive, I will not explain what does it mean, but the primitive characters are the real characters, so to say. The other non-primitive are less important. Okay, if K is primitive, then the Dirichlet L function is an entire function on C, has no poles, is holomorphic everywhere, and satisfies this similar functional equation. The point is that it relates values at S and chi to values of 1 minus S and chi bar, conjugated character. Another important example of an L function is Dedekind zeta functions of algebraic number fields. So let K be an algebraic number field of degree n, discriminant D of K, and the ring of integers OK. These here numbers E1 and R2 are the numbers of embeddings of the field into complex field of complex numbers. R1 is number of real embeddings, and 2R is the number of complex or non-real embeddings. So this 2 comes from the fact that whatever embeddings we have, conjugated mapping is also an embedding. So there are two pairs of okay, there are one pairs of conjugated embeddings. And for this object, we have the following product. Here, the local factor is similar like in the case of the Riemann zeta function, but the product is taken over all non-zero prime ideals of this ring. Okay. And let us observe that this equality here between product and the sum is equivalent to the statement that OK is a Dedekind domain. So again, important property of the ring is somehow encoded into this analytic formula. Okay, we can generalize it and consider Hecke characters of class groups and have any. So I will skip a bit this example from. Okay, there's no time to go into these details, but all these functions have similar properties to the Riemann zeta function, but proofs are really more complicated. They admit analytic continuation to the whole complex plane. Dedekind zeta function has a simple pole at s equal to 1 with the following residue. And look at this residue. In the residue of the Dedekind zeta function, we see the most important constant associated to algebraic number field. So class number, age, numbers of embeddings. K is so-called regulator of the field. Decade is discriminant, as I said before. WK is the root of roots of unity in K. So the order of the torsion part of the group of units of the ring of algebraic integers in K. So if the characters are non-trivial, the corresponding zeta functions are entire and they satisfy the functional equation. In particular, for the Dedekind zeta function, functional equation looks like this. A bit more complicated. There are many gamma factors here, but in general, this is a very similar functional equation like that of the Riemann zeta function. So this is Riemann type, as we say, functional equation. Another example, the final example of L function is Hasse-Weil L function of an elliptic curve. So let us look at the elliptic curve over Q. For primes not dividing conductor, I will not define conductor, but for P not dividing this number, EP, coefficient EP is equal to P plus 1 minus number of the order of local elliptic curve associated to P. So the reduction of P mod of E mod P. For P dividing, the conductor coefficients are defined a bit differently in a more complicated way, but we skip the subject. And then we have the following product. This is, so for primes not dividing conductor, the local L function looks like this. And the product, this is the affinite product. So this, from analytic point of view, this is not that interesting. So this is metamorphic and so on. So convergence problems are only with the first product. And this product converges absolutely for sigma greater than 1. And this function admits an analytic continuation to C and satisfies a functional equation with a single gamma factor. This was proved by Andrew Wiles. And this property implies the truth of Fermat-Last theorem. So this fact, the checking that this L function has good analytic properties is really non-trivial. Okay, Riemann zeta function has zeros at negative even integers, and they are the only zeros on the half plane, negative half plane, and they are called trivial zeros. And moreover, it has infinitely many zeros, which are denoted by rho. Rho is beta plus I gamma, and beta real part is between 0 and 1. They are called non-trivial zeros. They are the most mysterious and important for analytic number theory. We have the following Adamat product. So S minus 1 times gamma times zeta. This is an entire function of order 1, this left-hand side. And the only zeros of this entire function, non-trivial zeros of the Riemann zeta function. So we have the following equality, and this holds for all S. In particular, for sigma greater than 1, we have the following very interesting and striking, I would say, even equality. Look how strange it is. On the left-hand side, we have known functions, so elementary S, S minus 1, gamma, S over 2. Okay, this is special function, but the properties are so well known that it can be regarded as known object or elementary object. And we have this product, which is Riemann zeta function, highly non-trivial, depending on the distribution of primes. On the right-hand side here.
Excuse me, and the product is all over primes? All
Yes,
primes? Yeah.
over
Okay.
all primes.
All primes, okay.
Over all primes. And here on the right-hand side, we have product over all non-trivial zeros of the Riemann zeta function. So you see that, in fact, primes and non-trivial zeros of the Riemann zeta function are dual objects. In this sense, if we knew everything about primes, about distribution of primes, we could, via this equality, read properties of the Riemann of the non-trivial zeros, and vice versa. So primes and non-trivial zeros of the Riemann zeta function are dual objects, and this is the main observation at the starting point of analytic number theory, of a large part of analytic number theory. So let us look closer at this phenomenon. Okay, pi of x, let be the usual counting function, so number of primes up to x. Von Mangold lambda function is the following one. Lambda of n is log p if n is a prime power and 0 otherwise. And Chebyshev psi function is defined like this here. And this is, in fact, we count here prime powers with logarithmic weights. Okay, and psi naught is given. This psi has jumps, so in jumps are exactly at prime powers, and psi naught is the function which is okay. It has arithmetic mean between left and right limits at the discontinuity. And Riemann von Mangold formula is the following one. For x greater than 1, psi naught is the sum. Yes, so psi naught is the following sum. And this is, in my opinion, something really beautiful, or maybe I would say that it is one of the most beautiful formula number theory, or even in mathematics. Look at the left-hand side, we have pure arithmetic object. So here we count prime powers with logarithmic weights, but it's not unimportant. On the left-hand side, right-hand side, we have no reference to arithmetic. We have pure analytic objects, some elementary function like x, this constant here, this logarithmic, which means nothing. And we have sum over non-trivial zeros of the Riemann zeta function. Really something very beautiful. For applications, it's better to have maybe less elegant, but much more useful truncated version of this formula instead of this series, infinite series. It's better to consider a finite sum, and t is a parameter, and we can choose this parameter in a suitable way to somehow to estimate this this sum. As a result, one can prove the following, that psi of x is asymptotic to x when x tends to infinity. So this equivalence means that the quotient of psi of x over x tends to 1 is equivalent to the statement that Riemann zeta function has no zeros on one line, so on vertical one line. And that means that real parts of all non-trivial zeros of the Riemann zeta function are smaller, strictly smaller than 1. In fact, this can be proved. This is a theorem now, this one. So we have that psi of x is asymptotically equivalent to x. And this is the same as saying that pi of x, the number of primes up to x, is x over log x. So quotient of these two quantities tends to 1 when x tends to infinity. This is, of course, the famous prime number theorem, but it's proved using non-trivial zeros. We can do better. So we can show that the Riemann zeta function doesn't vanish in certain strip near one line. So this is one line, and this region is like this. So to the right of this Riemann zeta function does not vanish, and this allows the following stronger result, that psi of x is x plus some remainder, which is of smaller order than the main term, and psi of x is asymptotically equal to the integral logarithm of x. This d of x is defined here. So there are better, so to say, versions of stronger version of prime number theorem. Riemann hypothesis asserts that there are no non-trivial zeros to the right of 1/2. This is unproved hypothesis. Well, very well known. Nobody knows how to solve it, but equivalently, it means that real parts of the non-trivial zeros are 1/2. And the Riemann hypothesis is equivalent to the following statement, that pi of x is equal to the integral logarithm of x plus this very good error term. This is square root cancellation in the remainder term. So nobody knows how to prove it. The Riemann hypothesis is regarded as one of the major open problems in modern mathematics. Okay, let me switch quickly to other.
Sorry, may I have a quick question?
Yes.
So if you could go back to the previous slide, I would like to compare these two error terms, one from this corollary and the second one from the Riemann hypothesis. So
Yeah.
here we have e to the power minus c1, but still there is a square root of log. Yes.
Yes. So this does not even give big of x1 minus epsilon to n epsilon. This is larger than this for n.
larger. Oh, okay, larger. Okay.
Large. This is not exponential because this is square root of. This is less. This is something like x over log x to n power.
Okay, I see. So this
So-
error term in Riemann hypothesis is much better.
Much better. Okay, let me switch to something which is more current, quantitative theory of factorization. So let K be an algebraic number field, okay, ring of algebraic integers, HK, the class group of K. AK, this ring OK is unique factorization domain if only if H is 1, so if the class group is trivial. In general, class group is the measure of deviation from unique factorization in K, in OK. For instance, if h equal to 2 means that there are algebraic integers in K, which with essentially different factorizations into irreducible factors, but every two such factorizations have the same number of factors. Then such ring is called a half factorial domain. So h equal 1 means factorial domain, unique factorization, UFD. F equal to 2 means half factorial domain. Larger h means there are bigger and bigger deviations from unique factorization. The main object of the quantitative theory of factorization is as follows. We are given a set A of in-person non-associated elements, and we want to describe behavior of the counting function. How many elements are in this set with an absolute value of norm less or equal than x? Yeah, of course, instead of A, we can consider the set of principal ideas generated by A. The same as looking at in-person non-associated elements, of course. Examples of such interesting sets are as follows. For instance, we can look at the set of the prime elements in OK, or the set of irreducible elements. So when H is greater than 1, these two sets are, of course, not equal. The set of elements with unique factorization, the set of elements with essentially different factorization, the set of elements with a unique length of factorization, and so on and so on. There are infinitely many possibilities. For every A defined using factorization properties, we can associate the so-called zeta function, which is simply sum over A in our set of 1 of absolute value of norm to the S power. And this converges for sigma greater than 1. And usually such zeta functions do not have good analytic properties. They may not have analytic continuation to C, or may not satisfy any fractional equation of the desired shape. But still they are useful. Let A not be the ring of functions which are holomorphic and bounded in the following half plane, sigma greater than 1/2 plus epsilon for every epsilon. And A be the set of polynomials over a naught in Dedekind or Hecke L function and logarithms of Hecke L function over all characters of the group of ideal classes. So this is polynomial in 2H variables evaluated at different points. So quite nice analytic object, but pretty complicated, I would say. The theorem is as follows. If zeta function of A belongs to this ring, then the counting function is asymptotically equal to the following expression, where pk are polynomials. We can also say something about degrees of this polynomials, but it's not that important. Now, let us look at the example. Consider the set of irreducible elements of K, and then Pj for every class Xj is this following set. So we sum over prime ideals from this fixed class of ideals. And for sigma greater than 1, this function can be written in this way. In fact, this formula, which looks quite complicated, is a corollary to orthogonality of characters in the group. Okay, anyway, mu here, mu is classical Möbius function. From this formula, it follows that Pj are in our ring A. Okay, one has to do some one has to know something about these functions to show it, but it's possible. Moreover, there exists a finite set V of the sequences of length h of integers, so-called the minimal relations in the class group, such that the zeta function of mk is the following quite complicated, still more complicated expression, where, remember, each factor here is complicated as well. You can see here, these are Pj. So this is really something which looks pretty complicated, but still it can be shown that from this formula that this zeta function belongs to A. Very good. That means that we have asymptotic formula for the number of irreducible elements in the ring of algebraic integers, and this formula is displayed here in the screen, and decay in the exponent is so-called the Davenport constant of the field. When k is q, then the number of irreducible elements is the same as number of primes. In that case, decay is 1, so this power of double logarithm disappears, and we are back in the following prime number theorem. So this is generalization of prime number theorem. Okay, I think it's no time to go further, so I will skip few slides here. So it's possible to prove something more about this, but let me go to the last subject which I would like to speak about in this talk. So let me explain what the resonance problem is, and this is something which is current in research. So suppose that we are given an L function, and let theta be a sequence of complex numbers of absolute value 1. And let us consider the following twist. So we hit an L function by this sequence. And we look what we obtain. Of course, if the initial sum is convergent for, say, for sigma greater than 1, so the absolutely convergent, this is absolutely convergent in the same half plane, so this is no problem. But for almost all theta, the twist does not have good analytic properties. Often the vertical line sigma equal to 1/2 is its natural boundary. But let us assume that the set of measure 0 of theta, not this one means that we make a trivial twist, so we don't twist the initial function. So let us consider this set of theta such that the twist is meromorphic on C, and suppose that it's not empty. The resonance problem is to describe theta in this set for which the twist is not entire. But let me explain why it's important. Interpretation of this is as follows. If the twist is entire, that means that this product here, coefficients times this test sequence, is a chaotic noise, no resonance. If the twist has a pole, yes, then the sequences an and theta n resonate. There is some conspiracy between them, and then and this is of course an important, because we usually coefficients of an L functions are important objects from analytic or geometric point of view. So if these two resonate, then that means that something interesting is going on. Let us look at a simple example. Let us consider the square of the Riemann zeta function, and then coefficients at the end. This is number of divisors of n, divisor function. So very nice. So the fact is following, which is not quite easy to prove, but possible, that for every alpha non-zero, the following sequence here belongs to S0. So that means that when we twist this function here, the square of the Riemann zeta function by this sequence, then we obtain something which is meromorphic on C. If alpha is not plus minus square root of m, where m is a positive integer, then this twist is entire. So for almost all n, we have a pure noise, chaotic noise, nothing happens interesting. But if alpha is plus or minus square root of n, then these functions have simple poles. And poles are at that points. That means that something is going on between divisor function and function which is given here, the sequence square root of n. And of course, something is going on. So let us draw the simplest possible corollary from this conspiracy. Well, so the question is, what does it mean for the divisor function? So for x tending to infinity, we have the following classical asymptotic formula for the sum of divisors over n up to x. This is the main term. And then we have a remainder x to the theta. Dirichlet showed that this easy proof that theta can be taken 1/2. Divisor problem is to compute the infimum of this theta. And conjecture is that that this infimum is 1/4. This is a mysterious conjecture because what is the reason? Why 1/4? What for? Why this is the limit? There should be a reason. So current record in estimating T0 from below is the following theorem by Martin Huxley. So this is still bigger than 1/4. So this conjecture is open. But we know that this twist here has a simple pole at s equal to 3/4. So because of this effect about conspiracy between square roots and the n. And from this, by a simple tool like partial summation, we see that theta must be greater or equal than 1/4. So that means that if theta would be smaller than 1/4, then there would be no pole at this point. So you see that this resonance problem has meaning for particular cases. So let me switch to the more exotic example, the elliptic curve. Let us consider the following elliptic curve over rationals. It has conductor 37. And the pass-avail L function is like this here. And of course, for sigma greater than 1, this is the sum Dirichlet series with certain coefficients. Here are coefficients AE of n, which are interesting objects from the point of view of arithmetic because they are related to the number of rational points on elliptic curves over finite fields. So the fact is as follows, that whenever we take alpha and beta, where at least one of them is non-zero, then the following sequence, very strangely looking, belongs to the set S of LSE. That means that when we hit coefficients of this function, so we twist them by this strangely looking complex numbers, we obtain something which has meromorphic continuation to the whole complex plane. That means that this is non-trivial analytic object. The fact is the following, that when we take a specific theta naught, then this twist here with this strangely looking coefficients is meromorphic on C and has a simple pole at that point. That means, and moreover, if alpha beta is different from these two values, but this point is sufficiently close to this, then this function is entire. So we have an isolated point where something interesting happens. So where there is a resonance between coefficients of pass-avail function and this strangely looking objects. Okay, so the question is, what does it mean for E? And the answer is that we don't know yet. But I hope in future we will understand what is going on and why these strange objects behave as I described. A great mystery for sure, an interesting problem for future research. Okay. Thank you for your attention.
Thank you for the talk. Are there any questions or comments? Adam, you would like to ask a question? Yes,
Yes,
please.
Yes, if I could, I would like to ask the following. So I would like to hear your opinion about this approach to Riemann hypothesis using this mysterious conjectured object, which is called a field with one element. So what is your opinion about it?
Yes, Riemann hypothesis. This is okay. Every approach is welcome to say, but we don't know if it leads to any conclusion or not. Right? There are two types of approaches to Riemann hypothesis. The more interesting, in my opinion, they give partial results. They give approximations to Riemann hypothesis, and therefore also allow to prove some non-trivial results. For instance, this which was in my talk, the non-vanishing of the Riemann zeta function on one line. This is, of course, very far from Riemann hypothesis, but this is a kind of approximation, right? And it gives prime number theorem. I value such theorems very high. The other approaches to Riemann hypothesis are 0-1, so to say, theorem. So they give either the whole Riemann hypothesis or nothing. And usually they give nothing. But
Okay.
it may happen. It may happen in theorem that one of the such approaches eventually will give the whole proof. That would be fantastic. Okay, I know few hundreds of equivalents to Riemann hypothesis of that time, and this is one of which that I'm not much excited.
Okay, thank you. I see.
Okay, another questions, please.
You did say that functional equation is some sort of duality statement. Can you tell more about this? Is it a
Functional equation?
yes? Functional equation as a duality.
No, I said that this approach to arithmetics via analytic methods, this is duality. So we switch from group to its dual, and we work in dual group, and then we go back and see what does it mean for arithmetic. This is the duality. Functional equation is not, I would not call it duality. No.
How would you call it?
Well, for me, this is Riemann-Roch theorem in adelic. In adelic, so to say, field of meaning.
Okay, any other questions or comments? Please.
I have one more question. So, of course, this Riemann hypothesis is very famous, and people already recognize how much this analytical structure is important in this problem. But suppose that I'm given some number theoretic problem. Is it somehow immediate to recognize whether this analytical method would be more useful than methods coming from, for example, algebraic geometry, which is also very powerful in number theory?
Yeah, good question. It's difficult to answer such question. In many cases, it's obvious that something can be done via analytic method. Okay, let me give example. subject which belongs to analytic number theory and also to algebraic geometry is solving Diophantine equations, right? And some of them can be approached purely geometrically, by means of arithmetic geometry or algebraic geometry. And results are splendid. The good example is Falting's theorem of what was done with exponential Diophantine equation. But there is a whole bunch of Diophantine equations which can be solved not without using arithmetic geometry or algebraic geometry, but using Hardy-Littwood circle method. And it's really difficult to judge just from the beginning which approach is better.
Okay.
So one has to experiment and well, having some experience, you can say no, Hardy-Littwood will not give any result because it would require too strong approximation of some exponential sums, for example. But also, it may happen that algebraic geometry for such cases also gives nothing or nearly trivial statement. Oh, but sometimes this algebraic approach is very powerful and efficient.
Sorry, and what about ergodic theory? Is also useful, yes, in number theories.
Yeah, it is. It is. Yeah, and now it's very much in fashion, I would say.
So this is yet another approach, possible approach.
Yeah. I think that number theory is a battlefield where tools of many branches of mathematics are useful.
Okay, thank you.
Okay, any questions from people on Zoom? No. So maybe I may have just some final question. So I understood that you like conspiracy, that well, we have a function and some conspiracy, and this says something because the function is not trivial, it's not entire. So what does it say for the initial problem in number theory, just generally? I mean.
Well, generally, I would say yes. Well, the goal of many researchers in analytic number theory is description of coefficients of L function, because they are directly defined in most cases by some algebraic, arithmetic, or geometric object.
Mm-hmm.
So we want to extract information about this object from the coefficients. So whatever brings us closer to this goal is welcome, because this twisting by unimodular sequences can be described in the following way. We have a bell, right? A bell, and we hit this bell by a sequence. And sometimes there is nothing. There is a noise, chaotic, nothing. But if we hit it in good point with a good object, there is a sound. This bell replies, and we can read the shape of this bell in some sense, right? So this twisting by unimodular sequences is just we throw something to object which is interesting for us and look what happened. And sometimes it's nothing, and sometimes in well-defined, discrete set of points, there is a response, so there is resonance. So that must say something about this object, but in many cases it's just so mysterious that we don't know what does it mean, but something is going on. So mathematics is developed. We have to understand what is going on.
Thank you.
Okay, I have maybe one more question, so if I could.
Okay,
Uh,
please.
So there was this famous meeting of, I think, Montgomery and Dyson, yes, on some conference, when they recognized that there is some similarity between what is happening in physics, in I think energy levels of heavy atoms, and the distribution of zeros of zeta. So in fact, later on, it turned out that there is some common reason for this, and the underlying reason is some universal randomness coming from the theory of random matrices. So could you somehow comment on this? So what is the role of this randomness underlying the behavior of the zeros?
Yeah, this subject was very popular some 10, 15 years ago. So random matrices and L functions, and people were very much excited, and a lot of results were proved in this direction. Well, the output of this is that we have now better conjectures about how, for example, Riemann zeta functions will behave like. For example, for moments, high moments of Riemann zeta function on critical line, there are some expectations drawn from the analogy between energy levels and distribution of eigenvalues of random large matrices and non-trivial zeros of the Riemann zeta function. So this direction of research is useful, but of course they give nothing to the initial arithmetic problem. Right? They are good. Well, they give some hints to us what should be the correct answer, what not. But okay, good for testing conjectures, I would say.
I've heard something like that, this Riemann zeta function could be somehow understood, obviously not completely, but some understanding could be given from the point of view of the so-called Adel class space, which involves all possible primes, but also the place in infinity. And somehow this random behavior would correspond to this place in infinity. So it's arithmetic, Archimedean place. So is it correct to think it in that way?
So you said that in Analytic, yes?
Yes, yes.
Okay. Well, this is a very well-known approach coming back to John Tate, who unified approach to L functions in Analytic setting. Well, this is from philosophical point of view, very important approach, and unifying ideas is important always in mathematics. We see the same pattern of sometimes of some objects or directions of research which seemingly are apart. Well, to be honest, now I cannot give any example of a theorem which can be proved using analytic approach and not proved by classical. So I would say that this approach is more theoretical and philosophical than practical meaning.
Okay, let's
Okay,
stop
thank you.
because it's very close to lunch. Okay.
Sorry.
So let's thank the speaker again.
Thank you.